Hello and welcome to the tutorial on the Pythagorean Theorem, where we're going to explore this idea that a squared plus b squared equals c squared. Now I'm sure many of you are familiar with this theorem. Whenever you're trying to find either the hypotenuse or a leg of a right triangle, you've probably used this on tests and homeworks and are very familiar with how to manipulate this equation to get whatever variable value you're looking for. But the purpose of this tutorial is to gain a deeper understanding of why this theorem works and where it came from, not necessarily practicing that it works. So let's dive right in. We have this window pane type of structure right here, where we're given side lengths A for this square right here, and we're giving side length C for this inscribed shaded square right here. Now if I asked you what the area of this shaded square is, you would probably tell me c squared, right? Because we're used to finding the area of a square. Given a side length, we know it's that number squared. But if I wanted you to tell me just what this triangle area is right here, kind of like in this top left window pane square, how would you tell me what that is? Well, we know that we have an area of a squared in this top pane. So we know that this triangle is 1/2 a squared. And we see that we have 4 of them. 2, 3, 4. Giving us an area of 2a squared. So c squared is also equal to 2a squared. It's made up of 4 parts, each of size area 1/2 a squared. Now here we have 2, and I guess essentially 3 identical areas. All I did from the previous page was take our window pane and shift the point over so that we have side length B along with our A and C. And I did the same with this square over here. This was still our original window pane from the previous page that I just shifted over. So they had equivalent areas. And what we want to do is find the area of this entire shaded region, the pink and the yellow inscribed square. So how would we begin to find the area of this structure? Well, probably the first thing and the most obvious thing is that c squared is somewhere in there, right? Because we have our square again with side length c, and we're very comfortable finding the area of a square and knowing that it's c squared, given that the length is c. Now looking over here, we see that we have a rectangle, AB, in which it covers, the pink or salmon covers exactly 1/2 of that rectangle AB. So much like in the previous screen where we saw we had 4 areas of 1/2 a squared, we see that we have 4 areas of 1/2 AB. Okay, so the area of this structure is c squared plus 2ab. Again, c squared is this inscribed square, and we have our 4 triangles 1/2 AB. Now let's get into what the Pythagorean theorem is claiming over here on this square structure. We have our a squared shaded in blue, and we have our b squared shaded in blue. And what the Pythagorean theorem is claiming is that the area of a squared and the area of b squared will equal the area of c squared. Now we know that the area of this entire structure we just found was c squared plus 2ab. Gives us the area of this entire structure. So what we're trying to do is find essentially c squared plus 2ab within these parts that were given. So we see our AB over here, and we see another AB over here, giving us our 2AB. Or if you even want to look at it as this being the white section right here being 1/2 AB, this is 1/2 AB, and then if you imagine kind of a dotted line dividing this in half, you would get 1/2 AB and 1/2 AB, giving us our total of 2AB. So if our area is c squared plus 2ab, and our 2ab constitutes these 2 areas right here, a squared plus b squared must equal c squared, given that the area is c squared plus 2ab. So that is where this Pythagorean theorem idea of a squared plus b squared equals c squared comes into play. And it is always true. You can see with the numbers at the top, I've already measured these. With these sections varying in size, a squared plus b squared always equals c squared.